We should be looking at a different topic today. Uh, Parallel lines, continuation to the previous video. So let's see what is it about.
U. So far, we have studied linear equations which describe lines in the Cartesian plane. In the next few lectures, we will explore several types of geometric relationships that can exist between two linear equations. One possibility is that the lines described by two linear equations can be parallel. As we have seen, any non-vertical line in the Cartesian plane can be uniquely identified by specifying its slope and a point which lies on the line. If the point falls on the y-axis, the equation of the line can be written in slope-intercept form. In this form, the constant m is the slope of the line, and the constant b is the y-coordinate of the y-intercept. If we write a second equation in slope-intercept form, which uses the same value for m, but a different y-intercept, both lines described by these equations will have the same slope, but no points in common. We say that these two lines are parallel to each other. Parallel lines have identical slopes, but no points in common. As a result, parallel lines on a flat plane never intersect. Let's say that we are given the equation for a line, and are asked to write a second equation for a parallel line which runs through a given point which does not lie on the y-axis. Since the two lines are parallel, we know that the slope of the second line must be the same as the slope of the first line. However, we cannot write the equation using slope-intercept form since we don't know the second line's y-intercept. However, we can use point-slope form since we know the line's slope and the coordinates x1 and y1 of the given point which lies on the line. It is easy to tell if two equations written in slope-intercept form describe parallel lines. If the slope m is the same in both equations, and b is different, then the equations describe two lines with the same slope, but which intercept the y-axis at different points. In other words, two parallel lines. On the other hand, two equations written in point-slope form, which have the same value for the slope m, may describe parallel lines, or they may both describe the same line, even when the two equations contain different values for x1 and y1. This is because the point represented by x1 and y1 in the first equation and the point represented by x1 and y1 in the second equation may fall on the same line. In that case, even though both equations look different, they actually describe the same line. Since in point-slope form, any one of an infinite number of points on the line may be used to determine the values of x1 and y1, there are an infinite number of different equations which can be written that describe the same line. So when two equations written in point-slope form have the same value for m, but different values for x1 and y1, how can we determine if they describe parallel lines or the same line? One easy way to test whether two equations with the same slope describe different lines is to find where each line crosses the y-axis. If the two equations intersect the y-axis at different points, then they do not describe the same line. On the other hand, if two equations with the same slope intersect the y-axis at the same point, then both equations must describe the same line. The y-intercept for each equation can be found by setting x to 0. The resulting value of y in each equation is the y-coordinate of each line's y-intercept. But different values for x1 and y1 with the same slope describe different lines is to find where each line crosses the y-axis. If the two equations intersect the y-axis at different points, then they do not describe the same line. On the other hand, if two equations with the same slope intersect the y-axis at the same point, then both equations must describe the same line. The y-intercept for each equation can be found by setting x to 0. The resulting value of y in each equation is the y-coordinate of each line's y-intercept. To solve the equations for y, we first eliminate the zeros and complete the arithmetic, multiplying 1/2 times -2 to get -1, and 1/2 times -6 to get -3. We then add 6 to both sides of the first equation and 8 to both sides of the second equation, allowing us to cancel the negative and positive 6's and the negative and positive 8's. Plus 6, 5. Y is 5. Therefore, both equations have the same y-intercept. Since the equations have the same slope and y-intercept, they both describe the same line. Now let's try this one more time, but with different values for x1 and y1 in the second equation. Once again, we find the y-intercepts for each equation by setting x to 0 and solving for y. We first eliminate the zeros and complete the arithmetic, multiplying 1/2 times -2 to get -1, and 1/2 times -10 to get -5. To rearrange the equation so that y is alone on the left side, we add 6 to both sides of the first equation and 7 to both sides of the second equation, allowing us to cancel the negative and positive. Completing the arithmetic plus value of y is different in each equation. Each equation has a different y-intercept. Since both equations have the same slope but different y-intercepts, they describe parallel lines. In this lecture, we have seen how linear equations can describe parallel lines. In the next lecture, we will see how linear equations can be created which describe perpendicular lines. To YU. In the last lecture, we saw how two linear equations could describe parallel lines in the Cartesian plane. Another possibility is that the lines described by two linear equations can be perpendicular. Perpendicular lines are lines which meet at right angles. At their point of intersection, two perpendicular lines form four 90-degree angles. Perpendicular lines don't have to be horizontal and vertical. They may be oriented in any way as long as they meet at right angles. So how can we determine if two linear equations describe perpendicular lines? As we saw in the last lecture, parallel lines have the same slope. Likewise, we can tell if two lines are perpendicular by comparing their slopes. Perpendicular lines have slopes which are negative reciprocals of each other. So what does it mean for slopes to be negative reciprocals? We saw in pre-algebra that multiplying two numbers that are reciprocals of each other always produces a product of 1. Negative reciprocals can be created by changing the sign of one of the reciprocals. Multiplying two numbers that are negative reciprocals always produces a product of -1. So if the slopes of two intersecting lines are negative reciprocals of each other, the product of their slopes must be -1, and this tells us that the two lines are perpendicular. So why are the slopes of perpendicular lines negative reciprocals? To see why this makes sense, let's draw a line running through the origin and place a point on the line somewhere other than the origin. The slope of this line can be calculated using any 2 points on the line, so if we like, we can use the origin as one of the points. The slope is equal to the difference in the 2 points' vertical positions divided by the difference in their horizontal positions. Traveling from the left point to the right point, let's call the difference in vertical positions P and the difference in horizontal positions Q. So the slope of the line is P over Q. Now let's create a second copy of this diagram, rotated 90 degrees counterclockwise. Since the copy of the line is rotated from the original line by 90 degrees, the two lines are perpendicular. For the second line, the slope can once again be calculated from the difference in vertical positions divided by the difference in horizontal positions as we travel from the left point to the right point. This time, the difference in vertical positions is -Q, and the difference in horizontal positions is P. So the slope of the second line is -Q over So this The slope of the second line is -Q over P. These two slopes, P over Q and -Q over P, are negative reciprocals of each other. We can prove that these slopes are negative reciprocals by multiplying them together. To multiply these two fractions, we multiply their numerators and denominators to create a single fraction. Then, moving the negative sign outside this fraction, and using the commutative law to swap Q and P in the numerator, we see that the numerator and denominator of the fraction are the same. So the fraction is equal to -1. These two slopes are therefore negative reciprocals of each other. This is true for any two perpendicular lines. That is, unless one of the lines is vertical, since a vertical line slope is undefined. Using the fact that the slopes of perpendicular lines are negative reciprocals allows us to construct an equation for a line which is perpendicular to any given line and intersecting any given point. For example, if we know that the given line slopes any two perpendicular lines, that is, unless one of the lines is vertical, since a vertical line slope is undefined. Using the fact that the slopes of of perpendicular lines are negative reciprocals allows us to construct an equation for a line which is perpendicular to any given line and intersecting any given point. For example, if we know that the given line any given is perpendicular to any given line and intersecting any given point. For example, if we know that the given line's slope is 1/2, then the slope of the perpendicular line must be the negative reciprocal of 1/2, or -2. We can then use point-slope form to write the equation of a perpendicular line through any given point. For example, let's say we are given the equation of a line and asked to write the equation for a perpendicular line which runs through the point 4, -5. Since the equation for the given line is in slope-intercept form, the coefficient of x, 3, corresponds to the constant m, the slope of the line. Since the slope of the given line is 3, the slope of the perpendicular line must be the negative reciprocal of 3, or -1/3. Knowing the slope and the coordinates of a point on the line, we can write the equation for the perpendicular line using the point-slope form. The constant m is the slope, -1/3, and constants x1 and y1 are the coordinates of the given point, 4 and -5. The equation can then be simplified by writing y minus -5 as y plus 5. We have seen two geometric relationships that can exist between lines described by linear equations. In the next lecture, we will introduce a powerful mathematical concept of finding solutions that simultaneously satisfy multiple equations. YU. So far, we have seen several types of geometric relationships that can exist when two linear equations are simultaneously graphed. Simultaneously graphing systems of equations like this is often a helpful tool in analyzing physical and mathematical relationships. In particular, the points of intersection of two graphs have a special significance, since the intersection points represent common solutions to both equations. To illustrate this concept, let's look at a race between a tortoise and a hare. As the race begins, the hare, engrossed in a fascinating chapter in his algebra book, decides to give the tortoise a head start so that he can finish reading the chapter on solving systems of linear equations. As the race begins, the tortoise starts down the road at 1/2 mile per hour, a very brisk pace for a tortoise. We can graph the tortoise's distance from the starting point as a function of time, letting the vertical axis represent distance and the horizontal axis represent elapsed time. We see that in the beginning, when the elapsed time is 0, the tortoise's distance from the starting point is also 0. After that, since he is traveling at a constant speed, his distance increases linearly as a function of time. Since the tortoise's speed is 1/2 mile per hour, after 4 hours, he has traveled 2 miles. 4 hours after the race has begun, the hare finally finishes his algebra chapter. Even though the tortoise has obtained a significant head start, the confident hare decides to take it easy. Since he knows that even casually strolling at 2 miles per hour, he will eventually pass the tortoise. So 4 hours after the race has begun, the hare is still 0 miles from the starting line. But from this point on, he travels at a constant speed of 2 miles per hour. Since the hare travels at a faster rate than the tortoise, the hare's graph has a greater slope. Looking at these two graphs, we see that throughout the race, the tortoise's distance increases linearly with time. And after 4 hours of elapsed time, the hare's distance also increases linearly. Until at some point, between 5 and 6 hours after the race has begun, the hare and tortoise meet. The point where the two graphs intersect represents the instant at which the tortoise and the hare are at the same place at the same time. If we can create equations for these two graphs, there are mathematical techniques which we can use to determine the coordinates of the point where the two graphs intersect. Knowing these coordinates, we can then determine the exact time and place where the tortoise and the hare meet. To create an equation for the tortoise's distance as a function of time, let's use the variable x to represent the time coordinate and y to represent the distance coordinate. We saw in the chapter on solving motion problems with linear equations that if we graph distance as a function of time for an object traveling at a constant speed, the slope of the graph will be equal to the speed of the object. So the slope of this line is 1/2. Since we know that this graph intercepts the y-axis at the origin, we can use the slope-intercept form to write the equation for this line. The value of the constant m in this equation is the slope of the line 1/2, and the value of b is the y-intercept 0. Eliminating the 0, we see that the equation for this line is y equals 1/2 x. Now that we have the equation for the tortoise's graph, we need to derive the equation for the hare. Since the hare is traveling at a constant speed of 2 miles per hour, the slope of his graph is 2. We don't know the line's y-intercept, but we do know that the line passes through the point 4, 0. So we can use the point-slope form to write the equation for this line. Filling in the values for the constants, we replace x1 in the equation with 4, y1 with 0, and m with the line slope 2. We can then simplify the equation by eliminating the 0 and distribute the 2 to the terms in parentheses. Multiplying 2 times 4 to get 8, we see that we now have equations for the tortoises and hares' distances as functions of time. It is important to remember that although the lines described by these equations extend infinitely in both directions, only the portion of the lines whose coordinates are positive are meaningful in this particular example. If we can now use these equations to calculate the coordinates of the point where the two graphs intersect, we will be able to determine the exact time and distance where the tortoise and the hare meet. In the next lecture, we will introduce a technique called substitution, which will allow us to calculate the unique coordinates which simultaneously solve both equations and thus find the intersection point of the two graphs. Is y equals 1/2 x, equal to the speed of the object. Let's use the variable x and then determine the exact time. To create an equation for the tortoise's distance as a function of time, let's use the variable x to represent the time coordinate. We saw in the chapter on function of time for an object traveling at a constant speed, this line accepts the y-axis speed of the object. So the slope of this line is 1/2. For this equation for the tortoise's graph, we need to derive the equation for the hare. Since the hare is traveling at a constant speed of and welcome tortoise and a hare. Read tortoise. Graphing their distances from the starting point as functions of time, we saw that the tortoise and hare each traveled at constant speeds. The tortoise, since the hare's speed was greater than the tortoise's, once he started, he quickly caught up, eventually passing the tortoise sometime between 5 and 6 hours after the race had begun. At the end of the lecture, we derived equations for these graphs, determined the coordinates of their intersection point, and thus the exact time and distance when the tortoise and hare meet. There are several different mathematical methods which can be used to find the points of intersection of two graphs. In this lecture, we will demonstrate a method called substitution. We know that the coordinates of any point on an equation's graph represent one possible solution to the equation. So the set of all points which make up the graph represents every possible solution to the equation. Likewise, for a different equation, the set of all the points which make up that graph represents every possible solution to that equation. Any point which lies on both graphs therefore represents a solution to both equations. We can find this intersection point if we find values for x and y which simultaneously satisfy both equations. Each equation tells us something about the relationship between x and y. For example, the second equation tells us that the value of y must be equal to 1/2 the value of x. We can substitute. This gives us an equation for y in the fill variable x. And on the we get 16x thirds. We can set the value of x in either equation to 16 thirds and find the corresponding value of y. Either equation will give us the same answer. So, since the second equation is the simplest, we will use it to find the value of y. Setting x to 16 thirds, we see that y is 1/2 times 16 thirds, or 8 thirds. We can check our calculated values for x and y by use of x and y's two graphs. Converting these fractions to mixed numbers, we see that this point represents an elapsed time of 5 1/3 hours and a distance of 2 2/3 miles from the starting point, and an elapsed time of fractions to mixed numbers point. So 5 hours and 20 minutes after the race has begun, the tortoise and hare meet 2 2/3 miles from the starting point. This method of solving a system of equations is called substitution. This name is appropriate, since, as we saw in this example, the value of y, represented in terms of x in one equation, is substituted for the variable y in a second equation. Is substituted for the variable y in a second equation. Is substituted for the variable y in a second equation. It can be substituted of solving systems of equations called elimination.